Okay. So today we are going to discuss our first example on Monte Carlo simulation. In Monte Carlo simulations, we use random numbers to mimic the processes. So let's see how we do that. Suggest a title for it: Monte Carlo simulation. Python comes with the random numbers. Right? The first one, which is available in almost all of the programming languages, even with Microsoft Excel and to your hand calculators, is the uniform random number generator. So it is just like that you have a small pieces of paper on which say several 100,000 numbers are written, right? And they are mixed together and you are picking one by one. I write here the library imports, import numpy as np and import matplotlib.pyplot as plt. In Python, the random numbers, there is one built-in random number generator, which is in the base Python package. That is from random library, but it gives you only one single random number at a time. So it is very similar to C random number or Fortran's random number. But to work with the vectors, we generally call with the numpy library. And then also they are available from the scipy library. Okay. So here, define X, say np random. So from numerical Python, call the sublibrary random and then call the function random. So the random number which will be generated, it is going to be just one single random number, right? You can repeat it several times. So it will give you the numbers, and these numbers are generated between 0 and 1. So say 5. So an array of random numbers would be created, right? So I'm saying it is uniform. So let me give you a proof for it. So I generate, say, 10,000 random numbers and make a distribution of it, right? So it is not very difficult. I define, say, n equal to 10,000, and I generate a vector S, a numpy random.random and random numbers, and correctly I say plt.hist in 20 bins, and I set color blue, right? So the random numbers have been generated, and we have got two arrays, one with the frequencies. The first array, if you see, the first array is starting with the numbers 506, 484, 518. These are the class frequencies, right? And we have the array of the class limits, and it starts from, say, almost 0 to 1, right? So you may also call for so these numbers are uniform, right? How to confirm it? You should apply the chi-square test, right? So that you can see within the prescribed confidence interval, it is uniform or not. So computer generates pseudo random numbers, and they qualify. They have been been tested for statistical test, so that we can consider them uniform and they are suitable for our calculations. Now, my first objective is to simulate the game of tossing coins. Tossing coins. So as I said from my earlier examples, like the game of tossing a coin is can also be performed by using a dice with 6 spaces. Can also be done with a deck of 52 cards, and can also be done if you have on small pieces of paper 1 to 1,000 numbers are written. So you can say, okay, if they are mixed together and we pick one by one, so let's designate numbers from 1 to 500 as head and the rest for tail, right? So on similar lines, let's do this game over here. So I'm going to use only the numbers. So I define heads, say equal to 1, oh, sorry, equal to 0. With these numbers, we have a vector S with random numbers, even though that is not required to store all the numbers in a vector. We call one by one. So let's do it one by one. So I say for I in range, n, and I call a uniform random number. Say I define variable toss. So toss is equal to numpy random.random. One random number has been generated. So I say now, if value toss is less than or equal to 0.5, right? So in that case, it's a head. So we update the values of heads and heads plus 1 and end of if statement, right? The moment I remove the indent, that will be over, right? In Python, there is no special end if statement, right? You just have to write from the just below the if statement, from the column where if statement has started. So that is also the end of for statement. So I remove the indent. Now I print the results. If I say probability is equal to n heads divided by n, right? And on the next line I call print probability equal to probability, right? So the answer is 0.4937. So the problem of tossing a coin has been reasonably simulated. But let's go one step ahead. Let's compute probability binomial process. Probability of finding 3 heads in 10 tosses, right? Probability of finding, let me give it a title first here, and I set it to a markdown. Three heads in 10 trials. So I create a new cell, and in that, let's define the total number of experiments. So I say 10 experiments, say 1000. In each experiment, I will define 10 values. So for x, so I say numpy zeros and 1. So 10 zeros in one row, right? I will fill this vector every time with the random numbers. Okay. So now, and I have to compute the successful experiments. So in which I say as 3 heads experiment, right? This is equal to 0. So this is to represent those experiments in which out of 10 we get 3 heads. So now I write for I varies from, right, say j varies from j in range n experiments, and each experiment, let me write one, let's write here, one experiment consists of n times tossing the coin. So I write x by random.random, and I say, okay. So 10 random numbers will be generated. Now I will count, right? So I write head count. It is for head count, it is equal to 0. And now I write if x of jj, if f of jj is less than or equal to 0.5, it's a head. So h count should be equal to h count plus 1. It is the end of the experiments, right? End of the experiment. We have counted the heads. Now the other condition, whether to accept this experiment or not, because we are interested in 3 heads experiments in which we got 3 heads. So I write now, if h count is equal to 3, right? If the number of heads in one experiment are 3, then S3 head is equal to S3 head plus 1, right? So this condition is also done, and then this has to be done for all 1000 experiments. Now the experimental definition of probability, or I would say it is the probability computed from Monte Carlo. Probability from Monte Carlo is simple. Number of times you got the desired success in your experiment divided by the total number of experiments. And I will compare it with the theoretical value. Well, theoretical value will come from the scipy function. We have to have imported that one. So let's import that one here. Okay. I first import scipy.stats as SPS. Okay. Because I will call the binomial function. So probability theoretical, that will be equal to scipy statistics binomial, then PMF, and for that case we have to provide the value of x. So we have said 3 heads in n trials, we said n, and the probability is 0.5, right? I hope I have written correctly. So let's print the values. Print probability from Monte Carlo, and on the next line I write print. Okay, let's give it a title. Probability Monte Carlo equal to, I write here probability theoretical equal to, this is from the formula. Okay, here we go. Monte Carlo and theoretical. Okay. Monte Carlo and theory. Monte Carlo programs require computational time. There is some error. Okay, actually, let me check whether there is some problem with the X definition. X np 0 10. Okay, that's the way to define. So there is the problem is from the definition of X. Right. Now let's see the, okay, it's done. So see the error, see the answers. Probability from Monte Carlo is 0.137. It is accurate up to 1 decimal place. If I improve the number of experiments, 10,000 experiments, so it has become accurate up to 2 decimal places. Monte Carlo works, and I'm still teacher. Professor Walter Lewin used to say, physics works and I'm still alive, because when he survived after his experiment, releasing experiment, pendulum releasing experiment, and it doesn't hit to him, he says, physics works and I'm still alive. So programming works, Monte Carlo works, therefore I'm still respectable.